Greetings and welcome, friends, boys and girls of all ages. Today we're going to talk about families of graphs. I kind of throw this in my introduction to calculus chapter, although arguably it's like from a far earlier chapter than this. But I only pull like a couple sections from it and toss it in the mix with the rest of them. So today we're talking about families of graphs, and if you have a family, well, you probably need a parent of some sort. And a parent graph is a graph that through translation, reflection, or dilation can give all the graphs of its family. So essentially this is the general idea. I guess I'll explain this concept. A parent graph for all parabolas would be like the y equals x squared graph, right? Something like that. So here's like y equals x squared. And that graph could be shifted up, right? So that would be like a translation. It could be shifted down. It could be a reflection, right? I could like mirror it and shift it. And I could dilate it, meaning I could stretch or smoosh it vertically or horizontally, right? So I could have all the wide parabolas or like the skinny parabolas, right? So all possible parabolas come from the parent graph y equals x squared. So instead of thinking about like these other graphs as like independent ones, we're going to start trying to think of them as modifications of the parent graph, because sometimes that can end up serving as a quicker means of graphing them, if I can think of the kind of macro concept that's going on. So as far as types of graphs that we're going to talk about, the first kind is the constant function, which is just a horizontal line. So you don't need to draw anything fancier than kind of like this graph that I drew right there for my note-taker friends. So this equation right here is the equation y equals x, if you're interested, right? So y equals x. Nope, I lied. That's y equals 0. Because the slope is 0, the y-intercept is 0, something like that. So it is constantly the same. I could shift that. I could do all sorts of crazy stuff. Another parent graph that we might talk of is the identity function, which is it's the parent of all possible diagonal lines. This is our classic y equals x friend right here. Y equals x, right? And if I mirror this, if I stretch this, right? If I stretch it, I could get like a steeper line. If I smoosh it, I could get a less steep line. I could reflect it and smoosh it, or all sorts of different things you could do. But that is the identity function y equals x. Polynomial functions, such as the parabola that I mentioned earlier, the y equals x squared. You could also have parent functions. Technically, I'd need a parent function for each degree polynomial. But yeah, so here's my classic y equals x squared graph. That's a terrible 2. If there was only one of them, so it wasn't the terrible 2s. Oh, classic. Although, to be honest, as a parent, not of a graph or a function, of a child, I gotta say, 2s haven't been so terrible yet, to be honest. But I guess he's only 2.5. Maybe he's storing it up for like the last 6 months for like a concentrated evil dose of children. Who knows? Here, this graph over here is the y equals x cubed graph, like so. And so I could stretch that, I could smoosh it, I could do a lot to that. I mean, some things are a little bit more complicated as far as the child functions to these, but you get the idea here. So I just want to give you a whole bunch of examples of the parents first. Square root function, you probably knew, is the inverse of a polynomial function. Now notice that I specified that it's a function, meaning that the bottom half of this actually cannot exist in order for it to be a function, because it would fail the vertical line test. So a square root function is just the positive square root, the principal root, if you will. So it's the top half of that sideways parabola. So yeah, this is actually, I guess I could write that down. That would be y equals the square root of x. And just the positive square root, like I said a moment ago. There's the absolute value function. which I think we've seen some of those before. I think probably back in the day. Nice way to memorize that is value has a V in it, and the graph looks like a V. How great! So I could, if I like stretch this, I could have like a narrower V, or I could smoosh it, right, and like it'd be like a flattened out V. I could mirror it, all sorts of stuff. Reflection is the more proper word for that. This next one is actually quite an interesting situation. I don't believe I've ever shown you this one before. This is the greatest integer function, which is a type of a piecewise function. And actually, maybe you could describe what is going on here. But this is, the function is y equals, and it's like these weird square double brackets of x. So it's like weird double brackets is the symbol for it. So the greatest integer function. So for decimal values between 0 and up to 1, notice it just rounds down to 0. For values from 1 up to 2, but not including it, it rounds down to 1. So it kind of like just truncates the decimal, essentially, right? So for 1.5, you just make it 1. For 2.1, you make it 2, right? And these little circles, these open circles, means that when I plug in 1, it is not equal to 0 here. It's actually equal to 1. So there's a jump up right here. And this actually is still a function. It passes the vertical line test, because if I was to draw a vertical line right here, it only is hitting this actual point because this is not a part of the graph. So this is the greatest integer function. Like I said earlier, it's a type of piecewise function. We'll look more at those later on in the next section. But things like this would be when you have maybe something like the classic example that I've seen is postal fees. That if you have a package that weighs, between a certain number of pounds, you just give it a flat rate for that, number of pounds. Like, okay, we're going to charge you this. And I could actually stretch this and smoosh it and flip it and do all sorts of things. But yeah, this is a very pattern-like, or I might even say linear sort of piecewise function. They can actually end up being much more disjointed, where I could have like this and then this. And like, so it's like part parabola, part line. So they don't have to be as sequential, if you will, perhaps. And then another type of function that is a good old parent is the rational function right here, which this is the equation y equals 1 over x, or x to the negative first power, if you want to think about it like that. And this, of course, has vertical and horizontal asymptotes present in it. And it is a function, because a vertical line would only hit a single point for every value except what value? Yeah, if I plug in this vertical line here, it actually would never hit the graph. But that's fine. The vertical, like for instance, if I look back at this guy, the square root function, right, here's a vertical line that doesn't hit the graph, and that's cool. We're fine with that, right? Hitting once, at most once, is the issue for the vertical line test. So those are all types of parent functions. Let's do an example of this and try to build some relationships to see if we could figure out some general strategies for this. So let's do our first little example. Now that we understand what parenting is like, let's see if we can do this. So graph f of x is equal to the absolute value of x, and g of x is equal to the opposite of the absolute value of x. So I'm going to graph these on the same plane. Why not, shall we? There we go. Yep. Oh. Yeah. Sure. Because there's going to be a relationship between, there should be similarities between a parent and a child. For instance, I have a giant cranium and my sons have giant craniums, right? They're like the 99th percentile. So that's what we're looking for is genetic similarities, perhaps, if you want to think about it that way. So let's see. The graph of f of x equals the absolute value of x is kind of like, well, you could view it as the y-intercept is at the origin. And imagine a line with a slope of 1, except on this side, then it is over here, because it's only ever positive. And actually, one of the things I'd like to point out about the absolute value graph is if this was not absolute value, if I just had y equals x, or f of x equals x, what would that have been? Yeah, it just would have been like this line, right? The whole way. And so notice the absolute value, what did it do? All of these positive values, it's like, hey, absolute value is lazy that day. It's not doing anything. It just leaves them the same. But any negative value, like here, pop it up there, right? Here's a negative value. Let's pop it right up there. Bam. So it took like the negative portion and just like threw it up into the positive side. And so absolute value graphs end up kind of doing some sort of like mirroring-ish effect, or like in this case it almost looks like it, you know, bounced right off the x-axis. So yeah, it just kind of mirrors whatever your negative values are ever and makes them positive is what the absolute value does. So what would g of the opposite of the absolute value of x look like? Upside down, right? So yeah, for a positive 1, now it would be negative 1. For a positive 2, now it would be negative 2. So yeah, the g of x function would be the negative kind of absolute value graph. So what is the relationship? What do you think putting a minus sign in front of my function did? Right, it reflected it over what? X-axis. Right. Good times. So, accurate, I would say. All right, so that's one type of kind of transformation, or, well, yeah, transformation that can occur. A reflection is a type of transformation. To our parent graph that I could kind of modify these. So that's the first kind that we might see. Let's do this example. Use the parent graph to sketch the following. So let me make a little grid here, something like. And let's see, the graph of the square root of x, I'm actually going to graph both the parent and the child at the same time. So let's see, the square root of x, square root of 0, 0, square root of, actually, I'll ask it this way, square root of 4 is 2. The square root of 9, 5, 6, 7, 8, 6, 7, 8, 9, there we go, is 3. So my square root graph would have looked something like this. Yeah, the square root of 1 is 1. Durr, I did know that. Durr. There we are. So that's what my square root graph would have looked like. What do you think adding 2 after my parent graph, after the function took place? What do you think that will do to our graph? Yeah, adding 2 to this y value would put me here. Adding 2 to this would put me here. Adding 2 to that would put me there. And 2 to that would put me there. So the child graph is just been translated by 2 units. So if I was to describe this, it was a vertical shift by 2, right, essentially. I shifted it up 2, right? So I'm able to get a completely new graph in its family, all right? So if I haven't described what the family of a set of graphs is yet, the square root family would be all possible variations of the square root parent, right, is what I'm describing in that situation. So here, this one's slightly trickier. Ooh, don't let it fool you. Oh boy, here it comes. Exemple. There we go. So, first of all, compare and contrast these two things for me, if you'd be so kind. Yeah, so this time I'm subtracting 4 from my input before it goes into the square root function. All right, so this one's actually going to be quite tricky, if I might say so myself. Does anyone have any thoughts, hypotheses of what might occur? To the left. And why do you suspect that? Because it's negative. And that is where this is deceptive. Oh man, it actually is going to shift it to the right. Well, it's actually related to, so let's see, here's the parent function. If I think about, when did I get 0 for this? When would my y value have been 0 for just the plain old square root of x, if that wasn't here? When x is 0. What would x have to be in order for me to get 0 under here again? 4. So at positive 4 is actually where I'm going to get that 0 value again. So in the case of when your addition or subtraction is on the inside of the function, or it's happening to the x value before the square root occurs, this was happening in my mind to the y value because the square root of x had already occurred. It's just shifting it up. It's going to shift it horizontally in kind of the opposite direction that you might first suspect. So I agree that that's not necessarily very intuitive. So this is a horizontal shift of 4 units. And my best kind of analogy comparison is for this, maybe if I do a little recall, you might remember y equals a parentheses x minus h all squared plus k. Back from like your math 3 days, where what was the vertex for this graph? It was actually positive h, positive k, where it was actually the opposite of this value, but the same as that value. All right, so the opposite sign occurs for the same reason that this is the opposite that you would first expect. All right, it's changing kind of what happened there. So don't be deceived by that. It's a sneaky one. Let's see. This one I'm gonna I might talk about this for you. Oh dear. Let's see, a little example. Man, I'm gonna run out of room fast. These graphs take up so much room. I was imagining that's what like a parent graph would say to her kids, like, you know, the children graphs. I'm like, clean up your room. Yeah, this is actually technically incorrect. They're supposed to be like all connected at the top. That is the greatest integer function that I talked about earlier. So that was like that little like step function where it was like this, right? And I'm going to just, well, actually, all right. So it's the step function. What do you think? Actually, oh, I've got an idea. Mr. Krabs, I have an idea. Let me just grab a snapshot of the parent, and then we'll talk about what we think will occur to the child. So here's the parent function. What do you think this 2 is going to do? Is this doubling the x value or the y value? The y value. I know that's kind of weird to think about it as, but it's doubling the y value because it's happening after the function has already occurred to x. Right? If the 2 is on the inside, that would actually have been a horizontal stretch. But since this is a 2 on the outside, it's going to be a vertical stretch. So for these values, doubling 0 is 0. Doubling 1, I would have this value. Doubling 2 would put me at 4, right? And doubling 3 would have put me at like the 6 value up here. So it's kind of like, it's not a shift, it's a stretch. What about doubling -1? Where would this point be? These points. Doubling -1 would be here. No, what's -1 times 2? -2. So that would be right here. Doubling -2 would put me at -4. All right. So this actually has changed kind of the slope in general of this, if you want to think about it like that. Actually, if I look at like kind of just the filled in points, it's kind of like those points are all on the line y equals 2x. And then any point that was a decimal just gets like thrown down to the ground because it's an adult. You can't tell me what to do. You're not my parent. You're not my real dad. I'm going to do what I want to do. Right? So yeah, so that's what that graph would end up looking like, its child and parent. So let me talk about some of these cases. Man, oh man, I'm so running out of room on this. It's not even funny. I don't know if I necessarily want you to have to write all these down. Summarize them maybe a little bit if you want. We'll talk about them. So the first kinds of changes are if I have the minus sign on the outside of the function, then it's reflected over the x-axis. If I put a minus sign on the inside, where it's happening to the x value prior to the function occurring, whether it's an absolute value function, whether it's a square function, whether it's a line. If it's happening to the x, then it's a reflection over the y-axis. So that's the first type of transformations that we can see. And then translations. And if you guys, well, I'll let you write this down. The people watching the video, they can fast forward. They'll scrub through this part if they really want to, right? Or they could go check out like some, yeah, let me promote another video channel. How about SciShow, SciShow is a really cool channel on YouTube. I also like Husky StarCraft, all one word. But he doesn't just play StarCraft these days. I also like Day9, DAY9, the number 9. Yeah, he's pretty good. He's actually a mathematician as well. You know, StarCraft 2 commentator, former pro player. Good stuff. Let's see. So let's look at these now that you guys got more of them written down. Translations. If I'm adding c after the function has occurred, it's a vertical translation. It's shifting up. Right? If I subtract the c value after the function has occurred, it's shifting down. If I'm adding c on the inside, so it's happening to the x before x got squared or absolute valued or greatest integered, it's shifting to the left. So notice that this is positive. Left we usually associate with negative, right? Because the x-axis, the negative x-axis is over on that side. And if I'm subtracting c to the x before the function occurs, then it's a horizontal shift to the right. Am I right? Am I right? I'm right. And the last kind, we've talked about vertical stretches before, and I think I used to call, like, say, vertical smoosh back in the day. But this is actually interesting for dilations. You can actually have both vertical and horizontal stretches or smooshes. And sometimes you can actually kind of convert from one to the other, the t'other. So if I'm multiplying the entire function by a number bigger than 1, it's a stretch, or it's expanded. If I multiply the entire function by something between 0 and 1, it compresses the graph. Now, if c was negative, then it could be some combination of a dilation and a reflection, because there's actually like hybrid situations where it's genetically different in multiple ways, if you want to think about it that way. And if I multiply the x value before the function occurs, by some constant, c, that's bigger than 1. And then it's a horizontal stretch, which actually is the same or similar to a vertical smoosh or compression. So that's kind of an interesting relationship. These two are similar to each other in effect, although the c values aren't necessarily the same in that situation. And if I multiply the inside, the x before the function occurs, by a number that's between 0 and 1, it's a horizontal smoosh, which is the same as a vertical stretch. So sometimes there's more than one way to perceive these problems. So let's see. So let's do one last example with 3 parts, A, B, and or C. So observe the graph of each function. Describe how the graphs relate. So all of these graphs are actually going to be related to one another. Question, well, you guys are probably still doing a lot of writing. We'll hang out for a minute. In the meantime, I'll sing me and Everett's favorite song, which is the Skyrim theme, in which he goes ba 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 ba, and that's like the best part of the song when him and I are both singing it together. And then sometimes we'll, like, instead of bubas, we'll say dadas, and it, man, really mixes it up. It's like, that's like, when we do that, I should shout out like remix, and then like, that would be so great. So, describe how the graphs relate. Now, what would the parent function of this guy be? Like, who's your parent, right? You find this kid wandering at a fair. Like, who's your parent? What do you think? Yeah, that's going to be related to the parabolas in Friends, right? And let's see, what do you think this minus 3 did? So it's been shifted down 3. And what do you think this minus 2 does to it? Ah, yes. In the opposite direction you might first suspect, right? Shift right by 2 units. So this has had kind of 2 things occur to it. And tell you what, this is what it would look like. Bam, right there. And I'm going to try to fit that like so. Ooh, man, I might even have to shrink that down a little bit more. So, right, so essentially it's been shifted down 3 units and to the right 2. I also could view that as to the right 2 and then down 3. Those would land me in the same spot. So that's what, it's exactly the same shape, but I could have stretched it or smooshed it as well. There's different things that could have occurred. So that's kind of cool, And I want you to think about, what would this look like here for part B? So the absolute value is wrapped around that. So that's going to be the absolute value of the y values because it's happening on the outside of the function. So maybe we'll, actually, yeah, ooh, I had another idea. Man, these ideas are so great. Yay, ideas. Let's see, so here we go. So here's the parent. So I'm taking the absolute value of the entire function. So that's positivizing the y values. So this y value here, what's going to happen to it? Well, it's already positive. It's above the x-axis, so that's going to stay the same. This one's going to stay the same. This one's going to stay the same. This one's going to stay the same. What's this one going to do? That's going to jump up here, right? And like this one's going to jump up here. And this one's going to jump up here. And then these ones are all positive, so they stay the same. So my graph, it's the same for those parts. And then this, it's like the parabola got like mirror imaged over that. And I get some like sweet, cool W for Waddy. That's fine. I have had some people suggest my videos to like their online classmates and be like, "Hey, check out this guy." So that can happen. Yeah. Well, someone told me that. I mean, I guess I can't believe everything I hear on the internet. It was a person on the internet that told me that.
Everything on the internet is true. Where'd you read that? The internet. And that one.
So here's the last part of the example. Y equals f of the absolute value of x. So now what I'm doing here is I'm positivizing the x values in a sense. So let me think about this. Okay. So what is the absolute value of 1? 1. And then if I plug in 1 into this, it's going to be the same there. It's going to be the same here. Absolute value of 3 is 3. 3 minus 2 all squared minus 3 is going to be the same value. All of these values are going to be the same on the right side of the axis. I think you'd agree. Now, what happens if I want to find the y value when I plug in -1? I'll get 1 and then plug it into the function. So at -1, its output is going to be the same output as I had when I plugged in +1. So it's going to be the same as this one over here. Or when I plug in -2, it'll be the same output I had at +2. So this one will be right here. And when I plug in -3, it'll be the same output as +3. So this one will be right here. And then I plug in, whatever this value is, that'll be the same over here. And it turns out I'll actually have another sweet W. Killer. Man, so great. So there we go. That's the general idea for these functions. And my name is Mr. Waddy. Bam. Ching. Thanks for watching, Internet friends. Bye-bye.